Okay, hello everyone. So we are going to discuss today about a little bit more about magnetism, magnetic field, sources of magnetic field. That's the main topic. Let's see what we have. So magnetic field due to a straight wire, and magnetic field, and then the force between two wires, two or more wires. How to define the unit of current? We're going to use magnetism to define current. Some applications, solenoid and toroid. These are special cases of wires that you wind them into coils kind of structures. Magnetic materials. What kind of materials do we use to make bar magnets, like permanent magnets, horseshoe magnets? What is this particular property that gives magnetism? It's called ferromagnetism. Some applications, and there's two other important terms comes with magnetism: paramagnetism and diamagnetism. We'll look into that. So these are the topics we're going to discuss. So let's start with magnetic field due to a straight wire. So we know that the letter symbol for magnetic field is capital letter B. We sometimes call it the B field, the magnetic field. The SI unit for measuring magnetic field is Tesla, denoted by T. Another unit for magnetic field is Gauss. That is little g, I believe. I have to double check. I normally don't use Gauss. But this is the standard, right? Tesla. Okay. So we talk about magnetic fields in wires, like in straight conductors. So if you have a conductor like this and you connect this to a battery, right, this other end also should go to the battery. Now there's a current going up. There will be magnetic field throughout these conductors, but let's pay attention to this portion here from, let's say, A to B. We know that we use the right hand rule, the first right hand rule, that you simply take your right hand and bend your fingers around this wire, and if you extend the thumb outwards, if this is the direction of current, these fingers that you wrap around the wire is the direction of the magnetic field line. So they're going to be little circles of magnetic field lines. Now the strength of this magnetic field decreases with distance. Right next to, anywhere right next to the wire, over here, like at this point, it will have some strong magnetic field. But if you anywhere near to that, it will be the same. You go a little over here, you make measurements, it will be a little smaller. You measure somewhere here, even smaller. Further away you go, it's smaller and smaller, right? So the magnetic field decreases with the distance. This, if you represent the magnetic field lines with these circles have some radius, right? As the radius r increases, magnetic field goes down. So how do you represent this using an equation? It is inversely proportional to the distance from the wire. So let's say this is the wire carrying a current I, and you want to find the magnetic field at some point here. The distance r, B, is given by mu naught I over 2 pi r. Magnetic field, I is the current, r is the distance from the wire, the perpendicular distance. Pi, you know what pi is, 3.14. Mu naught, here we have a new constant. Constant mu naught is called the permeability. permeability of free space, right? Remember, we talk about this epsilon, permittivity of free space. How much electric field is allowed to travel through the medium, permittivity. That's how much it's been permitted to go through a medium. That is for electric fields. When it comes to magnetism, we use the word permeability, right? Permeability of free space. And for space, or mostly for the atmosphere, the value is mu naught value is 4 pi times 10 to the negative 7 Tesla meters per ampere. Okay, so that's the idea of mu, and this is the equation. All right, let's try an example. Let's see what the next slide is. Okay, let's try this example. Calculation of B near a wire. Alright, so an electric wire. So we have the wire, current is going up, I is 25 amps. Magnetic field due to this current at a point 10 centimeters due north of the wire. Well, for me it looks more like east, right? At this point P, what is the magnetic field due to this current at point P? Forget about this north part. At this point, which is 10 centimeters from the wire, what is the magnetic field? Alright, so the first thing is, let's do the math and find that out. B is mu naught I over 2 pi r. Mu naught is 4 pi times 10 to the negative 7, right? So let's go back and check that. Negative 7 multiplied by current 25, 2 pi multiplied by distance 0.1. Here we see that pi and pi cancels out, 2 2. So we have so this is 1 times 10 to negative 1, makes it negative 6. 2 times 25, 50 times 10 to the negative 6, 5.0 times 10 to the negative 7 Tesla is the magnetic field at this point. Oh, made a mistake here, it's 10 to the negative 5, not 7. Okay, alright, so here we use the equation, pretty straightforward. Current, the distance given, plug into the equation. The reason why mu, permeability given as 4 pi 10 to the negative 7, we can easily give this as just another number. If we find what is 4 pi is, 4 times pi is 12.56. 4 times pi is this, times 10 to the negative 7, so 1.256, 10 to the negative 6. That's mu naught as a numerical value. Why do we put a pi here? By putting a pi, one advantage is the equation has 2 pi on the bottom, so pi and pi cancels out, makes the calculation much easier. The other thing is, if you use it as a numerical value, you might put 2 decimal points, 3 decimal points, 4 decimal points, whatever. But when you plug in pi, it's much more accurate. You can directly type in pi into the calculator. It takes care of like 8 decimal points. So the calculations are more accurate. Okay? So that's that. Alright, so we found the value of the magnetic field. At this point, it's 5 times 10 to the negative 5. What's the direction of the magnetic field? Now for that, we can use this first right hand rule. Place the thumb over here pointing up, that's the direction of the current. Wrap the fingers around the wire, some kind of weird hand, but you see that fingers are making a circle like this around the wire, right? So that means on the left side, this is the left side, this is the right side of the wire, this is the left side of the wire, right side. On the left side, the magnetic field, the fingers appears like coming out from the whiteboard, from the page towards you. So on this side, the magnetic field is coming towards you, represented by dots all over here. This side is all dots. A dot means, a dot and a circle means coming out. On the right side, fingers appear like they're going into the board. So the magnetic field should be all crosses. So at this point, that itself is a cross. Okay, it's going into the board. So if we want to verify that this value changes with distance, let's calculate V field at 10 meter distance. This is 10 centimeter. How about somewhere here 10 meters at this point over here? So note I over 2 pi r, 4 pi, 10 to the negative 7, 25, 2 pi, 10 centimeters, cancels out, 250 makes it 5, so this has 5 times 10 to the negative 7. 100 times smaller, right? So it decreases as you go further away from it. Okay, let's move on. Alright, here we have an example. Two parallel straight wires 10 centimeters apart carry currents in opposite directions. So in this diagram, the circle and a dot inside, it's a wire that coming out from the board or from the book, from the page. 10 centimeters away from it, there's another wire over here. Current is going into the page, right? So I1 is out, I2 is in, and this is I1 is 5 amps, 2 is 7 amps. Determine the magnitude and the direction of the magnetic field halfway between the two wires. So they are 10 centimeters apart. So this midpoint 5 centimeters from each wire. So let's give it a try. Now if the current is coming out from the board, I1, what is the direction of the magnetic field it creates over here? Let's say the midpoint is, let's call it point P. So I1, here's a wire, we are looking at the cross section coming towards us, right, I1. So what do? How do I explain this? Take your right hand, extend the thumb towards you, pointing at you, and bend your fingers, bend the other fingers. It's like you're grabbing the wire, wrapping your fingers around the wire. It's like you have your pen in your left hand, you put the right hand, put the fingers around it, and thumb is pointing towards you. So the fingers should wrap around like this. Thumb is coming out. Can't draw it, so thumb is coming to you. So that means the magnetic field is making circles like this. So at this point, 5 centimeters away. The magnetic field created by this I1 current at this point, 5 centimeters away, right? Going up. It's going up. So let's call it B1, going up. Now think about I2. Current is going into the board. Place the thumb directly pointing away from you and bend the fingers around the wire. So the fingers will be like this. That means the current is going in this direction. So 5 centimeters away from the wire, pointing up. So over here, it's pointing up. B2. So we have two magnetic fields pointing in the same direction, so you can add them. So if calculate them separately, B1 mu naught I1 over 2 pi r R1 5 centimeters, B2 mu naught I2 over 2 pi r. So you can do the math, figure out the numbers, add them together. When you do that, let me check the answer real quick. The answer together, I believe it's 4.8 10 to the negative 5 Tesla. Okay, see whether you can get this. Alright, what else we have? Magnetic field due to 4 wires. Here's a conceptual example. So the first diagram, 1, 2, 3, 4. The first 2 wires, it's going into the board. The bottom 2 wires coming out from the board. Let's assume that the currents are same and the distances are all same in the corners of a square. So question is, in which configuration, A or B, is the magnetic field greater at the center of the square? So yeah, think about it. See whether you can figure it out conceptually. Let's move on. Force between 2 parallel wires. Alright, let's give a try. Let me clear this. So these are all different examples of the same principle. The basic equation we use here is this: B equals mu naught I over 2 pi r. And we are trying to use it in many different situations. So here what we have is 2 parallel wires. In this example, they're carrying current in the same direction, both going up. 2 different currents, I1, I2. What is the force between the 2 wires? Can these magnetic fields, now we know that when there's a current in a wire, it creates magnetic field around it. The second wire also has its own magnetic field. Can these 2 fields interact with each other and make force, create some force between them? So let's give a try. Let's focus on the first wire, I1. So using the right hand rule, we see that it's creating a magnetic field so it's little circles like this, right? It's creating a magnetic field that comes out from the board on this side. These are all dots, I'm drawing dots, and goes into the board on this side. Alright, okay. So this I1 is creating this particular magnetic field. So the on the left, on the right hand side, the magnetic field B1 is going into the board. These are crosses. And we can find this B1 magnetic field. Let's say, what's the magnetic field right around here, next to this second wire, at a distance, let's say the distance between them is, we use the letter D instead of R. Alright, so we can write B1 is mu naught I1. I1 is what's creating it over 2 pi d. Now let's think about the wire I2. Let's think about that equation we learned earlier. If you place a wire in an external magnetic field, here's a wire carrying current I, the length of the wire is L, it's in an external magnetic field B, the force acting on it, force is BIL sine theta. If the magnetic field and the wire are perpendicular, this thing becomes 1, so it will be BIL. Now let's think about this wire with the current I2, right? It is in an external magnetic field created by the first wire. That external magnetic field is B1. The wire, let's say the length of the wire is L, right? We take this segment A to B. That length is L. So for I2, second wire, the external magnetic field is B1, right? Because the first wire is creating it. Length is L. Current through it is I2. Now using this equation, the force acting on it, and the other thing, are they perpendicular? Yes. If you think about when you place the right hand over here, you bend your fingers, the magnetic field directly going into the board over here, and wire is perpendicular to that. So we can say the force on the second wire, let's call it F2. Magnetic field, current, length. Magnetic field is B1, current is I2, length. B1 is mu naught I1 over 2 pi d, I2, length. We get mu naught I1 I2 L over 2 pi d. Let me write it over here. F2 is mu naught I1 I2 L over 2 pi d. That's the force on the second wire due to the first wire. What's the direction of this force? Come here, focus here on the second wire. Use the proper, the second right hand rule with all three fingers, right? Current is going up, index finger, current, middle finger into the board. Middle finger is in the direction of the mag field, so it goes into the board. This is the middle finger, magnetic field. The force, when you align your fingers like that, the force is automatically pointing this way. The thumb force is in this direction. Alright. Now, you do the same thing to the first wire. The second wire is creating its own magnetic field around it. Using the simple right hand rule with the bent fingers, you see that magnetic field around the second wire is coming out, kind of magnetic field. So if I draw it again, this I2 is creating a magnetic field that comes out. All dots around the first wire. So that creates a force. Apply the same thing. You will end up having the same equation. Naught I1 I2 L over 2 pi d. All the terms are same, means the two forces are same. If you calculate the direction, it's pointing this way. So the two wires are kind of pulling on each other. They are attracting each other if the current is in the same direction. Right? So the force between the two wires given by any one of these equations, we don't need to say F1 or F2, it's going to be the same F for both of them. So mu naught, the two currents, the length of each wire, divide by 2 pi, the separation between them. Give it a try by yourself. See what happens if we switch the direction of currents. What's going to happen in the force? It will be away from each other. But try to prove it. That's important. You might have a question like this in the exam. Okay, so this is what happens when two parallel wires carrying current in the same direction, opposite direction. There's an attraction between them. Alright, let's move on. So let's work on this. Here's the same thing. Same direction, attraction, opposite direction, repulsion. Here's the problem. Give it a try. Two wires 2 meter long, 3 millimeters apart, appliance cord, carrying a current of 8 amperes, DC, calculate the force, one wire. Okay. Right, let's try the next one. Suspending a wire with current. So, yeah, give it a try. I'm not going to say much. I want you guys to try this. Let me give you the solutions for these two problems. Alright, hold on. So it looks like the answer for this question, the force of one wire exerted on the other is 8.5 10 to the negative 3 newtons, I believe. See whether you can get the same thing. The next question, the current in I2 should be 15 amperes. Okay. Alright, what's next? Definition of ampere and the coulomb. So we don't need to worry about any math here, just need to have some idea about how the ampere was defined. Now we say that 1 coulomb of charge per second is 1 ampere. That's how we defined it earlier, the amount of charge. But it's very difficult to count a coulomb of charge, right? It's not easy to count it accurately. And then we use that somewhat inaccurate method to define the current. But later they developed a much better way. 1 ampere is defined as the current flowing each of two long parallel wires 1 meter apart. So you take two wires, place them 1 meter apart from each other, which result in a force of exactly 2 times 10 to the 7 newtons, 10 to the negative per meter of length of each wire. How much current do we have to have if we put in equal current on each wire? How much current has to be there when the wires are 1 meter apart and make this much force? That is 1 ampere. Then you define the coulomb. If you have 1 ampere going for 1 second, that's the amount of charge. That is 1 coulomb. Okay? Alright, what's next? Okay, so here's some applications. We'll discuss this in the next video. Alright, thanks.